Hi everyone, my name is Sindhu Raghunandan and I will be walking you through my work for the course project for the Machine Learning Foundations for Product Managers course on Coursera. And so in this project we were tasked with building a predictive model to predict the electrical energy output of a combined cycle power plant based on four main variables: the temperature measurements, ambient pressure measurements, relative humidity measurements, as well as the exhaust vacuum measurements. The target variable we were trying to predict is the net hourly electrical energy output, or PE. And so just to walk you through my process, after loading in the relevant libraries and the data set itself, I then went into some exploratory data analysis. So you can see that in this data set, we have about 9,568 entries or measurements across all four of those variables that I mentioned above. And then when looking at the Seaborn pair plot that shows the correlation between all the variables in the data set, you can start to see some correlations between our data and the target variable. Specifically, AT and V show strong correlations with our target variable PE, whereas AP and RH don't show as strong of correlations. And so that's important to keep in mind as we progress to building and testing our model. The other thing I did in exploratory data analysis was to look at whether there were any blank or NA values in the data set, and given that there were no blank values, there was no need for additional data imputation or changes. I then also looked at the distribution of the output energy column in the form of a histogram, as well as the summary statistics, and found that the mean output energy is around 450 and the standard deviation is around 17. And again, these will be important when we're evaluating the effectiveness of our model. After that exploratory data analysis, I then went into training, building the training and test data sets, and to do that I used the scikit-learn train test split function, which then creates your training and test split. I then trained the model using a linear regression model, and my rationale for doing this was based on the linear relationship between the AT and V variables with our output variable PE. And once I trained the model, then I went into predicting the energy output in our test data set, and plotted the predicted energy output to the actual energy output. And you can see that there's a pretty strong correlation, which suggests that the model is pretty effective in predicting the energy output based on how we've trained the model. Now, in order to evaluate the model, I then looked at the mean absolute error, mean squared error, and root mean squared error, and found that the mean absolute error is around 3.6, mean squared error is around 21.0, and root mean squared error is around 4.5. I then continued to explore which of the variables had the biggest impact on the predictive power of the model. And so I took out the two variables that were that didn't show a strong correlation with our target variable. So I removed AP and RH and ran the model again, and found that the errors actually slightly increase compared to when all four variables are included in the predictive model. I also tested what would happen if we remove the strongest correlated variables, AT and V, and as expected, the errors jump up pretty significantly without those variables included. So the last thing that I want to say is that the linear regression model from scikit-learn package was used to predict output energy based on AT, V, AP, and RH. Whether or not the model is successful enough can only really be determined by a true power plant subject matter experts, but based on my assessment, the standard deviation of PE across all measurements is 17.5 megawatts, and the root mean squared error is significantly lower than that at 4.5 megawatts, suggesting that the model does have some predictive power. Also, the 4.5 megawatts root mean squared error is 100 times lower than the average PE value, which is around 450, again suggesting that this error is negligible and the model is a reliable predictor of output energy based on ATV, AP, and RH. To further probe, I played around with removing the variables that were less correlated based on visual inspection of the scatter plots, and found that removing AP and RH does not decrease the root mean squared error by a significant amount. It actually increases the error a little bit. However, removing the strongly correlated variables, AT and V, does significantly increase the root mean squared error. So this might allow us to conclude that AT and V, the temperature and vacuum, are the stronger predictors of PE. And again, based on deeper subject matter expertise, we may be able to use this information to design a better combined cycle power plant. So that's all I had. Really enjoyed the course and the project. Thank you.